Continuity is one of those topics where it's more of common sense rather than calculus, but continuity is that the idea that if you were to draw the graph of a function, then you can draw that graph without having to lift up your pen or pencil at all, and also that you wouldn't have to retrace over a line. So there's three conditions that a function must have in order to satisfy that it's continuous on a closed interval from a to b, and that's that f of c is defined, the limit as x approaches c of f of x exists, and that the limit as x approaches c of f of x equals f of c. So just to see it in a sketch of a graph, let's say c is 2. So f of c is defined. That would satisfy number 1. Number 2, the limit of f of x as x approaches c exists. So that means that the limit from the left is going to be approaching 2, and the limit from the right is going to be approaching x equals 2 as well. And then number 3, the limit as x approaches c of f of x is going to equal f of c, which you defined in number 1. So that just means that the graph is going to run through that point. And then you can now say that this function is continuous at x equals 2. There are two types of discontinuities. The first one is the removable discontinuity, and that's when if f can be made continuous by appropriately defining or redefining f of c. So usually this occurs when there's a hole in the graph, or f of c is not defined. So say you are given a graph such as this one, and say, just make that 2 again. This would be a removable discontinuity because you can make f continuous if you just redefine this point into that spot right there. Then the function would be continuous all the way through. So when trying to determine if your function has a removable discontinuity, the way that I think of it when you're solving it algebraically is if you can remove a factor from the numerator and the denominator, then there's a removable discontinuity within the function. So here's just an example. G of x equals x squared minus 1 over x minus 1. Well, first thing you would want to do is just factor it out. So the top is a difference of 2 squares, x plus 1, x minus 1, all over x minus 1. And I'm just going to put this in parentheses so it's easier to see it as one factor. And so from here you can see that your x minus 1s can cancel out, and all you're left with is x plus 1. Now the fact that you cross these out means that there's going to be a hole present in the graph, and a hole is indicative of a removable discontinuity. And because you notice that you removed a factor from both the denominator and the numerator, then that also indicates that it's a removable discontinuity. So if you were to say the question was asking, state any discontinuities within the function and determine whether they are removable or non-removable, then to answer this question you would write removable discontinuity at, and it would be x equals 1. And that would be your answer. The other type of discontinuity is the non-removable. And that's when it is not possible to make the graph f continuous by redefining f of c. This usually occurs when there's an asymptote involved. So for a graph, say say you had a graph that was like this. Well, it's obvious that there's some sort of discontinuity at 2, but what you're trying to find out is if it's non-removable or removable. And because you can't just redefine a point to make this graph continuous, since it never even touches 2 because there's an asymptote here, and then also this one's going to positive infinity while this one's going to negative infinity, then you can't just plug in a point somewhere or move a point somewhere and make the graph continuous. That means that it's a non-removable discontinuity. So say you were given the problem f of x equals 1 over x plus 1. First you just want to look to see if there's anything you can cancel out or factor, and in this one you can't do anything. So then remember, to find a vertical asymptote, you look to the denominator and set it equal to 0. So if you go x plus 1 equals 0, x equals negative 1, and this would be your vertical asymptote, which would also be where there is a discontinuity. And because you didn't remove anything from the numerator and denominator, it would be a non-removable discontinuity. So when you're stating your answer, non-removable discontinuity at x equals negative 1. There are also some instances when functions will always be continuous, and those are there's 4 of them. When function the first one is polynomial functions. No matter the degree, polynomial functions will always be continuous. The second one is rational functions. So long as say it was f of x over g of x, as long as g of x does not equal 0. In that case, there would be a non-removable discontinuity. The third one, radical functions. So anything with some sort of root. And keep in mind that these are within the domain. So for radical functions, they're always continuous within their domain. And the last one, trig functions. And just like radical functions, those would apply to like tangent, cotangent, cosecant, and secant. They're continuous within their domain. Not saying continuous everywhere, but it has to be able to be within the function's domain.